using these right here. Okay, so here's what we've got going on today. We've got all these real world situations that are going to be coming up, and there's different types of models, formulas that use exponents and logarithms to describe different sets of data. Okay, so you guys are familiar with exponential growth and exponential decay. Okay, those are two that you have dealt with a lot, right? Exponential growth would be like you're putting money in a bank. Well, PERT, right? PERT would be an exponential growth situation. You put money in a bank, it gets interest, so it grows, so it's going to go up. And this is what an exponential growth graph looks like. So this right here is exponential growth. All right. Exponential decay would be the exact opposite. Instead of something, okay, well, first of all, let's look at the exponential growth. It is increasing, but it's increasing at an increasing rate. So that's how you would describe a graph of exponential growth. So it's increasing, but at an increasing rate. Think of a couple of rabbits that are on a deserted island, and then they start multiplying, right? So you start with 2 rabbits, and then by the end of the year, you have a bajillion rabbits because they're growing at an exponential rate, right? A bajillion might be an exaggeration. Sorry, I like to use that word. Is it really a word? Anybody know? Is bajillion?
I don't think so.
No? Okay. All right, so exponential decay is used in situations such as, you guys have all gone through science and you've learned about half-lives, okay? The half-life of like carbon dating, that's like how much carbon is left in an object after so much time. That's using exponential decay, and what's actually happening is it's decreasing, but it's decreasing at a decreasing rate. Okay, that's exponential decay. Another use for exponential decay is if you have medicine in your system. So let's take, say you take some medicine at 8 a.m. That medicine is going to start wearing off, and it's going to be going wearing off at a decreasing rate. So we'll be talking about some of those exact, problems later on. All right, now this is a Gaussian model. It's sometimes called the bell curve. And this is used like, you think of a bell curve and you think of natural, like in teaching, we always think that there's, you've got all these grades across the board. So you got the A, B, C, D, E, no, A, B, C, D, F, okay? Normally you have a bell curve with your grading. So I'm grading some tests. I should have a fewer number of Fs over here, Fs and Ds. Then I should have more C's and B's in this range, and then I'm going to have fewer A's up here. Okay, so that would be like a bell curve. This right here, this is the logistic model, and this is, notice you have an asymptote right up here. That would be like, there's a limiting number. It's increasing, some value is increasing, but it's only increasing up to that asymptote. It gets closer and closer and closer to that, but it'll never quite reach it because it's a number that you can't get to. This would be like, I think we've had a problem before where it was talking about trying to get rid of the pollutants. You have a big business, and how much money is it going to cost to get rid of pollutants? You can never actually get rid of 100% of those pollutants. It's like an unreachable goal. You can get close to it, but you can't quite get there. Does that make sense for those?
Which one? What is that called?
That is the logistic model. So the logistic model is right here. So the two that are basically, okay, the logarithm, these are both logs. So we've actually dealt with the logs before. And remember, a logarithmic model, the log is the inverse of the exponent. So if you have this guy, remember how inverse graphs flip over that x equals y? These two right here are the inverse of these two right here. Those are exponential graphs and logarithmic graphs. The Gaussian and the logistic are the two specialty ones, okay? Now, if you look at the Gaussian model, I mean, it's like complicated because you have this e to the power of something, but then it's got a power in the power. So it's got like a power to a power. And then the logistic one has this fraction. So it's like a rational with exponents. Okay, so that's the difference between those. So what I would do is I would make, if you were going to make yourself a set of flashcards, what I would do is I would make one set of flashcards that has this on one side, so these names on one side, and then the equations on the other. And then I make another set of flashcards that has the name on one side and then the graph that goes with it on the other side. And if you wanted to get crazy, you could even do the equation on one side and the graph on the other side. But you need to be able to go from all three of those, you know, get the name, the equation, and the graph. So you need to be able to get to all of those. Does that make sense? Are we good with these? And again, I will work on this after my classes are all done for the day. I will try to see if I can get some of those made up, okay? And then I'll push them out if I do get them done. Any questions on these? So you have the bell curve, that is the Gaussian model. And then the, it almost looks like a flat line, but it does have a curve in there. So it's increasing at an increasing rate, and then it increases at a decreasing rate. So it kind of flattens out. If you did this on your graphing calculator, it would look like something like that. So it looks pretty flat at the top, pretty flat at the bottom, and then it has that increasing section in between. All right, I've been talking a lot. Anybody want to ask a question or make a statement?
I have no questions.
Okay. Thanks for being the, you're always the spokesperson. I appreciate
I
that.
hate doing that because I feel bad. Like, what if someone has a question and I'm just like, no questions, let's go. And they're like, wait.
Well, then they should speak up, right?
Well, yeah, but I feel bad.
Oh, you're good. You're good. I bet you anything. Okay. Everybody else, did Parker speak for you?
Yeah.
Yeah.
Yep.
Okay. See?
Somebody do my job for me sometimes.
All right, so you guys, we have two examples to do and then we're done. So example 1 says it's a population increase. Estimates of the world population in millions from 1995 through 2003 are shown in the table. The scatter plot of the data is shown in figure 3.29. All right, so you have these years, 1995 to 2003. An exponential growth model that approximates this data is P equals 5,340 e to the 0.012922 t, where 5 is between, or t is between 5 and 13. That would be for year 1995 through year 2003. All right, now it says compare the values given by the model with the estimates given by the US Census Bureau. According to this model, when will the world population reach 6.8 billion? Okay, so figure 3.30 is actually doing that first part of the problem for you. If I were doing this in my graphing calculator, you want me to just go ahead and do it in the graphing calculator? Or are you guys all good with that? We don't need to spend the time.
Yeah, we're good.
Okay, so I would make list one.
Thank you.
Good job, Bobby. Parker appreciates that. All right, I would make list 1, 5, 6, 7, 8, 9, 10, 11, 12, 13, and at list 2 would be 5,691, 5,769, etc. Okay, then in your equation, you can just go ahead and put this whole thing into that equation, and then this is what would have popped up. Of course, you would have had to change your window because our X values would be from 5 to 13, but our Y values would have been from like 5,500 to 6,500, somewhere around there. And then you would have gotten something similar to that. Okay. The second part of that question says, according to this model, when will the world population reach 6.8 billion? All right. Well, this is in millions, right? So is that actually billion then? So I would put 6, 8, 0, 0 in for P. Maybe. And then I would have to use my skills that I learned in the last section, how to get T by itself, because I need to find out what year it's going to reach 6.8 billion. Or actually, what year it did reach 6.8 billion, because this is all in the past, because this is an old book. All right, so how would I do, what would I do to solve this? Anybody? How would I solve for T? Yeah, how would I solve for
Oh.
T? What would I do first?
Divide.
Yep, let's divide. All right, so we're going to divide both sides by 5340. And anybody have that number?
1.273.
Okay, 1.273 equals e to the 0.0129222 t. What would be the next step in this process?
Raising
Natural
that
log
to a
both
natural
sides.
log power.
Yeah, let's do ln of both sides, right? Which is that base E. Okay, ln of both sides. This goes away. That leaves me with 0.0129222 t over here. And I can go ahead and put ln of 1.273. What is that approximately? Because I'm not going to get the exact answer. Because
0.2414.
0.2414. All right, the only thing left to do then is divide by this big long number on both sides, which leaves me with approximately, anybody?
18.68.
All right, 18.68. All right, let's just round that to 18.7. 18.7, which would be year what? Let's see, year 13 was 2003. So somewhere in 2008. So in the year 2008, we're going to reach that. Oh, wait. Somewhere in the year 2008, we did reach that. Okay, sorry. I just always think it's funny when we're predicting stuff in the future, but it's really in the past because our book is so old. Okay. Any questions on that? Now, do you understand why we did all of that, the previous section? Because we're actually using it in real life situations.
Yeah.
Yeah. All right, you guys, one more. We have a modeling of population growth in a research experiment. A population of fruit flies is increasing according to the law of exponential growth. All right, I'm just going to say it. I hate fruit flies, hate them. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? Okay, so here's what we know. We have an ordered pair to 100. We also have another ordered pair, which is for 300. This is not a linear pattern, so we're not going to use y equals mx plus b and solve for the slope and the y-intercept and then use that information. We are going to make an exponential growth equation. So if we go back to the first page, our exponential growth model was this. So we have y equals ae to the bx, okay? So we're going to use that as our pattern. Y equals ae to the bx. Now, we know e is an actual set number, approximately 2.7, right? That's an irrational number like pi. So e is going to stay in our formula. Y and x are always going to be in our formula. So it's our job. We need to solve for the a and the b, because those are the two things we don't know. Okay, so I'm going to make two equations. I'm going to make one equation that uses this x and y. All right, so I've got 100 equals a e to the b times 2. All right, then I'm going to use another equation that has this in it. So that would be 300 equals a e to the, I'm going to just put it in the right order. Let's do that. I'm going to change this one up too. Okay, now here's my problem. I still have two unknowns. I need to figure them out. I'm going to use something called substitution to figure this out. All right. So if I take this one right here and I rearrange it so that I have it solved up for a is actually equal to 100 over e to the 2b. Is everybody with me how I did that?
Yeah.
Okay. The other one we're going to do the same thing with. So this time we have a is equal to 300 over e to the 4b. Because they're both equal to a, I can set them equal to each other. So I have 100 over e to the 2b equals 300 over e to the 4b. And why would I want to do this? What's the goal right now?
Solve for B.
Absolutely. So how can I do this with this proportion that I have set up? What can I do to solve this? Remember when we did cross multiplying because you had proportions? This multiplied together equals this multiplied together. So I can take 300 times e to the 2b, and that equals 100 e to the 4b. So now what can I do?
Divide
Yep.
100.
All right, so if we divide both sides by 100, we get 3e to the 2b equals e to the 4b. All right, now I probably would go ahead and divide both sides by e to the 2b. So that gives me 3 equals, now when you divide things with the same base, what do you actually do to the powers?
Subtract.
Yep, so we actually have e to the 2b because 4b minus 2b is 2b. Now I can go ahead and ln both sides to get rid of that e.
Isn't E divided by E1?
Yeah, but they have powers here. You can't do that.
Oh, okay.
So you got to subtract. It'd be like x to the 5th over x to the 3rd. What do you do?
Oh, yeah, okay.
All right. So we're going to take ln of 3. Oh, I should have used a bigger eraser. It's 1.099. That canceled off the ln of e, so we get 2b, so we can divide by 2. And that was a lot of work just to find out what b is, because we still have to find out what a is. So b is 0.5495. Now, what we actually found is the growth rate up here of the those fruit flies. So b is 0.5495. That goes here. All right, we're not done yet though. Here, I'm going to use my eraser. Let's go up here. Good news is this is the last example for the day. Okay, so I'm just going to use the first one. 100 equals a, because we still don't know a, e to the point, oh, I can multiply, right? Let's just do 0.5495 times 2. So that gives me 1.099. Okay, so is everybody good with what I just did?
Yeah.
Yeah.
All right, so now I have to divide by e to the 1 point. Okay, so I'm going to take 100 divided by e to the 1.099, and that gives me my a. So 100 divided by e to the 1.099, and I'm getting approximately 33.3 flies. Well, I can't have 33.3 flies, so I can have 33. So my A, my starting value of flies would be about 33. Okay, now, here's what we can do. We can go back up here to this equation, and we can write it in with our values. We have 33 here, and we have 0.5495 t, right? X, sorry, X. Okay, so how many flies will there be after 5 days? What do we do to find that?
Plug 5 for X.
Yep, we're going to put 5 in right here. We're going to take 0.5495 times 5, which is 2.7475. I'm going to take e to that 2.7475 power, multiply it by 33, and that's going to give me my approximate number of flies. Anybody get that? How many flies there are? Yes, no, maybe. You want me to do it on my calculator or not? Are you good?
We're good.
Okay, so I can throw your homework on the board here. I'm gonna type it though, since that'll be easier. Page 243, 1 through 6, 8 through 12 evens, 19, 20, 24 through 28 evens, 32, 35, and 38. Okay.